Have you ever wondered how the very first electronics got their power? Yeah, it wasn't as easy as just plugging something into a wall. See, deep inside the first electric motors and generators was this small but absolutely brilliant device that solved a massive problem. Today, we're going to pull back the curtain on the commutator, a clever little mechanical switch that literally changed the direction of electricity. So, here's the big problem we're trying to solve. Anytime you spin a coil of wire inside a magnetic field, the electricity it creates naturally wants to flow back and forth, back and forth. We call that alternating current, or AC. But back in the day, motors and batteries couldn't use AC. Nope, they needed direct current, or DC, a nice, steady flow that only goes in one direction. So the question is, how do you take a current that wants to alternate and force it to march in the straight line? To really appreciate just how genius the solution is, we first have to get to the root of the problem itself. Let's take a quick look at why a simple spinning generator spits out that back and forth current in the first place. It's all about the physics of just spinning around. Okay, so this is the fundamental rule of the game for making electricity. Just imagine these invisible lines of force stretching from a magnet's north pole to its south pole. That's your magnetic field. Now, when a wire moves and cuts through those lines, a voltage gets created, and that voltage pushes the electrons to start flowing. That's it. That's the core idea right there. All right, let's put that principle into action with a really simple generator. What we've got here is just a single loop of wire, and it's spinning between a north pole and a south pole. As the sides of this loop, let's call them AB and CD, as they rotate, they are literally slicing through that magnetic field, and that's what's going to generate our voltage. So let's follow this thing for one full rotation. When the coil is perfectly horizontal, at the 0 and 180 degree spots, it's moving parallel to the field lines. It's not really cutting them, so the voltage is 0. Makes sense, right? But when it's vertical, at 90 degrees, it's slicing through those lines at the fastest possible rate, and that gives us our peak positive voltage. Then it swings back down to 0. At 270 degrees, it's vertical again, cutting at max speed, but look, it's moving in the opposite direction through the field, and that reverses the flow, creating a peak negative voltage. And what you get from all that is this beautiful, classic sine wave. The voltage smoothly rises to a positive peak, falls back through 0, hits a negative peak, and then comes back to 0 again. This, right here, is alternating current. And this is our problem. So, how in the world do you take that perfect AC wave and force it to only flow in one direction? Well, you introduce an incredibly clever and surprisingly simple mechanical switch. Let's meet the hero of our story, the commutator. And you know what? The solution itself is almost deceptively simple. It's just a metal ring that's been split in two. You have these two copper halves, C1 and C2, and they're separated by this tiny little insulating gap, usually made of mica. As we're about to see, that tiny little gap is where all the magic happens. The source material really just nails it with this quote. A rectifier is any device that converts AC to DC. And the commutator, it does that exact job, but purely with mechanical action. It's a physical switch that literally flips the connections at the perfect possible moment. So, how does this little split ring actually pull off its electrical magic trick? Let's break it down moment by moment. This is the cool part. Okay, pay close attention, because this is where it all comes together. Focus on the diagram on the left. This shows the first half of the coil's rotation. See the spinning commutator at the bottom? And notice those two stationary blocks pressed up against it? Those are carbon brushes. They don't spin. They just sit there and make contact, carrying the current out to our circuit. Okay, so for the first 180 degrees of the turn, let's trace the path of the current. It flows out of the coil, through segment C2, through our external circuit from Q to P, and then comes back into the coil through segment C1. Pretty straightforward so far. Now for the absolutely brilliant part. As that coil passes the halfway point, the current inside the coil naturally reverses direction, right? We saw that with the sine wave. But, and this is the key, at that exact same instant, the commutator segments have spun around and swapped which brush they're touching. So get this, even though the current inside the coil has flipped, the commutator has flipped the external connections to perfectly cancel it out. The current flowing out to the load is still going from Q to P. It's an absolutely perfectly timed mechanical switch. The internal AC has been rectified into external DC. Just incredible. So what does this output actually look like now? We started with that smooth AC sine wave. What does the commutator's clever little flip actually give us on the other end?
And here is the big reveal. On the left, there's our original AC wave, dipping into the positive and the negative. But on the right, with the commutator doing its thing, look what happened. The entire negative part of the wave has been flipped up into the positive zone. So now the current only ever flows in one direction. But it's not exactly a smooth ride just yet.
And here's what that resulting waveform looks like. You can see it's basically a series of positive humps. The voltage rises from 0 to a maximum, falls back to 0, and does it again, twice for every single rotation of the coil. We call this pulsating DC. It's definitely direct current, it's unidirectional, but it's not that smooth, steady DC you'd get from, say, a battery.
All right, so now that we get the principle, and we've seen its action up close, let's zoom out a bit and see where this super important component actually fits inside a complete DC machine. This diagram pretty much shows the whole shebang. You can see the outer field poles creating that big magnetic field. You've got the central armature with all its windings where the voltage is actually created. And right there, connecting the spinning armature to the stationary brushes, that's our commutator.
So really, all DC machines, whether they're making power as a generator or using it as a motor, they're all built from these same core parts. You need the field system for the magnetism, the armature and its winding to spin inside it, the brushes to make contact, and of course, the commutator to do that crucial AC to DC conversion. They all have to work together in perfect harmony. You know, the commutator was this brilliant physical, mechanical solution that powered the entire first electrical revolution. But that spinning, sparking switch, it's long been replaced. Today, that exact same AC to DC conversion happens silently inside almost every single electronic device you own, and it uses solid-state parts with no movement at all. It kind of makes you wonder, doesn't it? What other noisy mechanical solutions of today will become the silent, invisible magic of tomorrow? Thanks for joining me.